Hello everyone, myself Dr. Srinivas Nallagonda, Professor and Head of the Department. Today I am here to discuss the MTech course Module 1, that is a PG Embedded Systems course, Hardware Software Co-Design. So this is a syllabus and overview of the syllabus. So this course provides a comprehensive understanding of hardware software co-design principles used in embedded systems and system on chip. It covers methodology for partitioning system functionality between hardware and software, exploring trade-offs in performance, cost, and power. So students will learn co-design techniques, system specification models, co-simulation, co-verification, and modern design flows used in real-time embedded system applications. So this is a course overview, hardware software co-design, and the prerequisite courses for this course is digital system design, microprocessors, and microcontrollers. The main objectives of this course are the students will try to learn hardware software co-design concepts, methodologies, and design flow, specification models, system level design, hardware software partitioning schemes, expertise knowledge on co-simulation, co-verification, co-synthesis, trade-offs between hardware and software implementation in embedded systems, designing of efficient, optimized, and cost-effective system-on-chip solutions. So these are the five objectives of this MTech course. So the course outcomes are as follows. So after successful completion of the course, students shall be able to understand the need and the principles of hardware-software co-design in modern embedded systems and analyze systems requirements and perform hardware software co-design partitioning effectively, model embedded systems using specification languages and system level design tools, and apply co-simulation and co-verification techniques for system validation, design hardware software integrated solutions for real-time applications and system on-chip design. So these are the course outcomes and objectives of this PG Embedded System course. This course is studying in 1-2 semester, that is the second semester of first year student. And we have total 5 modules. Module 1 is co-design issues, and module 2 is prototyping and emulation, and target architectures will be discussed in this module. And module 3, compilation techniques, tools for embedded process architectures. And module 4, design specification and verification. Module 5, language for systems. Co-design issues. So here we have subtopics of co-design issues. Co-design models, architectures, languages, a generic co-design methodology, code synthesis algorithms, hardware software synthesis algorithms, hardware software partitioning distributed system co-synthesis. So these are the subtopics of this module, that is the co-design issues. So introduction to co-design issues. So co-design, simulation design, simultaneous design of hardware software components of an embedded system, that is called co-design. Means we are simultaneously we are designing both hardware and software components of the embedded systems, and it aims to optimize performance, cost, power consumption, and development time. And the need for co-design, increasing the system complexity, shorter product development cycles, efficient utilization of hardware software resources. Benefits: improved system performance, reduced design iterations, and better resource management. Co-design models are, it describes interaction between hardware and software. For example, behavioral model, structural model, data flow model. Co-design architectures, hardware and software mapped onto a common platform. There are some types of common platforms like single processor architecture, multiprocessor architecture, distributor embedded system architecture. So co-design languages used to specify system behavior. Examples: System C, Spec C, VHDL, and Verilog. So generic co-design methodology, steps in co-design methodology. So system specification, it defines system requirements and functionality. Modeling, so create abstract system models. Partitioning, divide task into hardware and software components. After that, co-synthesis. So these are all steps in co-design methodology. Okay, so system specification is required. After that, modeling, then partitioning. Co-synthesis means generate hardware and software implementations, and integration and verification, so it tests complete system functionality. And finally, goal. Okay, so if you want to design any embedded system for a specific applications, so these steps are very very important, and these methodologies must be followed. And finally, our goal is to achieve optimal trade-off between performance, cost, and power. Co-synthesis algorithms. So here we have co-synthesis. What is the meaning of co-synthesis? It is nothing but automated process of generating hardware and software form a system specification. So the objectives of this co-synthesis is minimize execution time, reduce hardware cost, optimize power consumption, measure task, hardware synthesis, software synthesis, communication synthesis, and scheduling. Advantages: faster design cycle and improved design quality and better hardware software implementations. So hardware software partitioning means here we are discussing briefly the methodologies of code design, all the steps. So briefly we are discussing now. This is one of the step, that is hardware software partitioning. It decides which functions are implemented in hardware, in software. So that is nothing but hardware software partitioning. Okay, so in hardware generally we need high speed, so parallel executions. But if you take software, so flexibility, low cost. Okay, so the hardware software synthesis algorithm analyze application task, it evaluates performance constraints, and partition task, optimize and verify. So distributed system co-synthesis, this is also one of the step for the embedded system development. So multiprocessor or nodes cooperate to execute the task, and focuses on task allocation, scheduling, communication optimization, resource utilization. So there are several applications for this hardware software partitioning is automotive systems, IoT devices, industrial automation, real-time embedded systems. Okay, so finally, what we are achieving, so using this hardware software co-design, we are able to design or develop an embedded system. So it will be useful for various applications like automotive systems, means where hardware and software both will be performed parallelly, and functional will be, all functions will be done parallelly. And also we can use these concepts in IoT devices and industrial automations. We know in industry also we use this embedded system, so that we can reduce the manpower also. And real-time embedded systems also one of the applications of this uh, hardware software synthesis and distributed system co-synthesis. So finally, what we have studied from this module, so we have studied design models, that is nothing but architectures, languages, so a generic co-design methodology, so co-synthesis algorithms. Okay, so I mean to say that there are some steps we need to follow for the development of embedded systems. So these are the topics we have covered for this module 1. Also we have discussed hardware software synthesis algorithms. Okay, and hardware software partitioning, distributed systems co-synthesis, and also we have seen various applications. Okay, and this is a course, hardware software co-design, and it will be very useful for designing embedded systems. And we next class we study module 2, that is prototyping and emulation. So in this we are briefly discussing prototyping and emulation techniques, and prototyping emulation environments, future developments in emulation and prototyping architecture specialization techniques, system communication infrastructure techniques, system communication infrastructure. So these are the different topics we are going to discuss in module 2 in upcoming class. And thank you very much for thank you everyone for listening this class. That is a module 1 co-design issues for embedded systems PG course. Thank you very much.